Thank you very much. So this talk is all about using motion sensors that we have in now phones or devices like Microbit, all kinds of other wearable devices, how we can program the data that comes out of them in Python and run some data fusion algorithms. So the reason why we want to do this is, particularly over the last couple of years, these sensors are now super small, they're really, really cheap, and that lets you build some really fun things with them. And particularly for Pycon here, it's because we can write the algorithms for them in Python. So for this talk today, I'm going to talk a little bit about how motion sensors have changed. The original gyroscope was in 1852, but what do we actually use today in 2016? And do an example of using a BBC Microbit as a wireless data logger. Have there been other talks today on the Microbit? Yep, good. So we can go quickly through that. And then look at a couple of examples of data fusion, where we combine data from multiple sensors. Be one example where we build a digital compass, and then another one that does a very quick outline of how to build a 9 degree of freedom inertial measurement unit using mobile phone data. So first of all, what are some of the applications for sensors? Why are they suddenly everywhere? So of course they're used in mapping, in virtual reality, where you need to track the movement of the head display, otherwise the person using it gets sick. On augmented reality, where you need to track the motion of the phone or the camera, so you can superimpose things in the right place. Motion capture, this is a guy who's wearing a motion capture suit. You'll see there are various points in the suit where there are little square things. So that's where the motion sensors are placed, and as he moves, the sensors beam back the motions that he's doing, and then an animation package can turn that into shots from a film or something like that. And here is a DJ in a nightclub in the Netherlands who's wearing a motion capture suit, and as he's playing his music, then there's an animated robotic version of him on the screen behind. That's a pretty cool application. Drone racing, of course. Drones have pretty tough requirements for knowing where they are, with algorithms that have very low latency to figure out where they need to go without crashing. And cars are another big application. In fact, cars were one of the original mass market applications for sensor technology to be miniaturized and improved. So here a collision sensor for airbags, for sort of fitness trackers and things like that, a fuel band and a Fitbit for those people that want to measure everything that they do every second of the day. Sports is getting into sensors in a big way, so I guess as top sports people do training more and more, they'll start to have these funny sensors stuck on the back of their head or on their arms or in a pouch in the middle of their back. Here's an application that you can get for an iPhone. It doesn't actually need any separate sensors, it just uses the movement sensors in the phone itself. It sits on the guy's arm as he's playing lacrosse, as he's flicking the ball, and it can count the amount of training that he does. Here's a motion sensor from a company called Zep. And you stick these on the end of golf clubs or baseball bats or tennis rackets, and it will keep track of the swings that you take or the number of shots that you take in tennis. And over on the left, it can track in 3 dimensions the movement that you're doing and even compare it against a library of movements from golf pros, and so you can see how well you compare like that. So that's just a very quick run through of some of the millions of different usages that sensors are popping up in now, that the technology has got really cheap, light, small, very battery efficient, and also quite easy to program. So what are some of the types of sensors that we're going to look at? So here is a list of the 5 main types. So a gyroscope, accelerometer, magnetometer, and GPS, and a pressure sensor. And then there's a lot of other things you can do with temperature and light and sound and things like that. The gyroscopes actually started, this is the first gyroscope from 1852, and it was developed by this guy, Foucault, who's perhaps more famous for his pendulum. He hung his pendulum from the roof of the Parthenon in Paris and showed that as the Earth rotated, the pendulum swung with the direction of the Earth, and so that appeared to move over the course of a day. The following year, he built this contraption that aimed to demonstrate it on a quicker time scale, and the principle is the same as that of a spinning top. So if you have a spinning top and set it down on the point, it spins fast, and the top will stay upright because of the conservation of angular momentum of the rotating disc. So in this contraption, you set the disc rotating. It will spin for about 10 minutes before friction kills it. In that time, the Earth will have rotated slightly, so this whole structure of the machine will move. It's on gimbals so that the rotating disc stays in the same orientation in absolute space, and so relative to the room it's in, it will rotate slightly, and that's read on this extended pointer and the dial there. So that's a very analog gyroscope, but it illustrated the principle. And in terms of size, you can see the telescope next to it, so it's about this big. If we wind the clock forward to 1965, this is what a gyroscope was in the Saturn V rockets. Basically, rather than a vertically oriented rotating disc, this has a horizontal platform, and that has gyroscopes, modules on corners of it, and those can tell when their orientation is going wrong, and then this will have motors that drive it back to be horizontal. So as your rocket takes off and flies through the air at an angle, you can use this to read off the angle of your machine. Here's a guy assembling one of them. So it's pretty large, a bit smaller than Foucault's, but pretty complex. And these were assembled ready for use by putting it in this metal canister and then fixing it here in one of the sections of the Saturn V rocket. And the actual place where it fitted is just up here. And this here is the nitrogen that kept it at a pressure of 13 psi inside. So you then took this big section of your Saturn V rocket, popped it on top of the main section of the rocket, put it on a launch pad, and you can fire it off. So that was what playing with sensors was like in 1965. Nowadays, this is what a gyroscope looks like, and it's quite a bit smaller. in terms of size, from here over to here is about 1 millimetre. And the way that it works is by a slightly different gyroscopic principle. Like if you have a tuning fork, probably people don't know what tuning forks are nowadays, but if you have a tuning fork with sort of 2 prongs on it, bang it on a hard surface and it will vibrate. If you try and rotate the tuning fork, you'll feel a slight resistance because of the Coriolis effect. So in this device, this micro-machined electromagnetic structure, what you have is this whole middle section can move, and we have drive plates on these sides here that make it vibrate at about 20,000 hertz, and then on the top and the bottom you have sensors where the plates will move a little bit closer together or further away. That will change the capacitance, and the electronics can read that. So you put a couple of those things together and you end up with a really teeny-weeny gyroscope that can measure angular velocity. This is another picture of the micro-machine structure in it. And it's really pretty incredible that you can build something like that, but the scale on it across here, 200 micrometers, the whole thing is less than a millimeter across, and you can build that, assemble it with the electronics, and distribute it and sell it for about £1 or 2. That's pretty amazing compared with where the technology was in 1965. So, given that this is what the technology is today, that's how the gyroscopes works. We won't look in detail at accelerometers and magnetometers, but they use similar kinds of MEMS structures. An accelerometer measures the acceleration on these small structures inside the chip, and that acceleration includes gravity. So you'll see that, yes, that does show up, that there's this G term here for gravity, which gets rotated by the angle of the sensor, and so what we read out in terms of X, Y, and Z coordinates includes that. Magnetometer is also constructed using the same kind of technology. That measures the magnetic field of the Earth, that then is rotated through 3 different planes, 3 different angles in the phi omega and phi theta and psi, and these are pitch, roll, and yaw angles if you are into flying aircraft or doing radar tracking. And then, because the magnetic field is really weak, we always have other ferromagnetic materials near the sensor that contribute their own magnetic field, and those have these 2 distortion terms for W and V for hard iron and soft iron, and that gives the total field that we read from our sensor. When we put these together in a device, we end up with a teeny-weeny chip on a microbit. So the chip on the microbit, the microbit's this big. Probably saw one earlier on, and the chip itself is just here. The microbit, the accelerometer, and the magnetometer are in 2 different chips. Here's another wearable, one from an American company called Ambient Labs, and it's a MetaWear CPRO. And this includes a gyroscope as well, and the gyroscope and the accelerometer are in two tiny chips. So I won't go through the specs for that. For the microbit, I mean, I find it totally amazing that you can get all of this functionality in something that, if you're at school, is free and if you buy it from a shop, it's about £12. That's totally astounding. So not only does it have a CPU that's capable of running Python, but it has a radio that lets us transmit data. Unfortunately, we can't use the Bluetooth part of it and MicroPython at the same time. It takes up too much of its memory, but we can use its other radio, as we'll see. Plus, it's got these two sensors. So, as an example, this show how to use a Microbit for doing wireless data logging and capture the movements. So this is a photo of my laptop at home, and on the laptop screen is a remote Microbit, which if I switch it on, so I have a data logging program in Python that's on here that's reading the sensors on it and is transmitting it wirelessly to the Microbit attached to my laptop. This is receiving it, sending it through the USB as a serial port, where I can then read the data on the laptop, capture that, and then analyze that to do some motion analysis. So this is each time it flashes, it's received another 10 packets of data. So what's in the picture here is, for this example, I wanted a source of motion that was relatively convenient to capture and had a change in state. So rather than getting some friends to go outside with tennis rackets or things like that, I stuck the remote Microbit onto the kettle in the kitchen with a rubber band, and then captured the motion of it as the kettle boiled. And so it creates small bubbles and big bubbles, and so that's a fairly repeatable but easy source of motion in 3 dimensions. To show you how easy it is to read this sensor data on Microbit, this is all the code you need. I mean, you know, it's the interfacing to all of these makes it so easy to do that you just think of all the great applications that you can do with it. The coding is something that just falls out without having to stress you. So to read the accelerometer values, we just call accelerometer.values. There's a gesture that the chip will detect, whether it's up or down, etc. So we can get that. For the compass, we have to read the X, Y, and Z values separately. There's also a compass heading that corrects for all the hard iron and soft iron distortions. We put that together in one string, and then we send it back. And the code to send it back is as simple as saying, radio, turn yourself on, and then in an infinite loop, we read the sensors, we send the data back, and then we sleep for a little bit. So in essence, this is all the code that runs on this remote Microbit. I can do a couple more things to do a flashing display so you can see that it's actually doing something, but in essence, that's all you need to do data logging. At the receiving end, the code that runs on the Microbit is also trivial. We just tell it to turn the radio on. We tell it to turn the serial interface on, the UART, run over the USB cable, and then in an infinite loop, we just wait to receive data on the radio. When we've got that, we send it off to the computer. You do that. You stick the sensor on the kettle, you boil yourself a cup of tea, get us a whole lot of data, and then we can analyze it in Python. On my GitHub site, there's a Jupyter notebook that shows this analysis and things like that. I'll go through the code very quickly because we've only got a few minutes. but it's really just to give you a flavour of how easy this is. So we can read in, this is using the pandas analysis package, which is normally imported as, abbreviated as PD. So pandas has functions for reading CSV files, so we just read it in. The structure of the file looks like what's on the bottom there. Then we can plot it with the X, Y, and Z coordinates of the acceleration. And you can see that the intensity builds up while the water is heating up. Then actually, as it gets close to boiling, the simmering gets more controlled and it vibrates less. And then when the water is actually boiling, then then the whole kettle doesn't shake much. So this is with the X, Y, and Z coordinates of the acceleration on the raw data. We can look at the power across those 3 dimensions and plot a power spectrum from that, which, if nothing else, shows a nice, colourful the transitions between the different stages of boiling. So you can do more analysis like this from other types of data that you collect. Here are some ideas for things you can try. But it's a lot of fun, and the Microbit makes it so easy. For data fusion algorithms, we have multiple sensors, the data is a bit noisy, and so we want to combine them together in an optimal way. Some of the ways of combining these sensors, we can build an electronic compass with an accelerometer and magnetometer, an inertial measurement unit with an accelerometer and gyroscope, and then if we add a magnetometer to that, then we have something that gives us absolute orientation. So here's an example of using the same setup with the Microbit for a compass. If we just use the plain magnetometer data, then and try and calculate the heading from that, then the angles are all go all over the place, and we need to correct for the if we correct for the tilt of it with some basic trigonometry, then we can get estimates of the heading that are much better. So that's another use. I won't go into the correction here. Here is a third example, which, if you don't have a Microbit, is another way to get sensor data from an Android phone. Here's a couple of programs that you can use to see what the sensors are, to stream the data over Wi-Fi, or to capture them locally to a CSV file, and then you can analyze that. And so if you want to put all 3 of those sensors together, you use what are quite sophisticated algorithms to combine them, detect errors, and then estimate the statistics of the results using something called a Kalman filter. I'm not going to go into that at all, except that there's a lot of packages where people in the drone community and so on have written to do this type of thing. So taking noisy 9-axis data on the left-hand side, and here is heading angles as I've held my phone and wiggled it up and down, walking in circles 3 times. So here is the angles wrap around 360 degrees as I turn in a full circle. But this is really simple to use. The maths for doing rotations is a bit cumbersome. These packages like this psykinematics or psychic kinematics makes it quite easy. And if you're enthusiastic about that, then try and use your phone data to build a full 9 degree of freedom IMU system. If you want some references to where to go for further information for all of this, here's some of the things that I referred to in putting this together. In particular, the data sheets here from sensors, the BBC Microbit, they're excellent not only for the hardware, but only for the theory of how to do data fusion and how to deal with all of the errors and things. So this is the end of the talk. The GitHub repo is here. It has the slides and some code. So check it out if you like, or come and talk to me. I'll be here all weekend. Thank you.
Thank you very much. We don't formally have any time left for questions, except, of course, there's nothing after this. So you should feel free to ask some questions. But before I let you do that, I'm going to let the speech-to-text people go. But we should give them a big thank you for their hard work today. Thank you very much. All right, do we have any questions?